All right, hello everybody. We are live with Chegg's Pre-Calculus and Algebra Office Hour. We're going to be here every week at this time at 6:30 Pacific Time, 9:30 Eastern Time to answer all of your questions about pre-calc and algebra. So welcome. We're excited to go through this with you today. I'm just going to push a little button here so make sure everything is working. There we go. And excellent. So for those of you that have joined us before, welcome back. This is I am Wallace Dem. Start with me. I am Wallace Dem. I am here with Chegg to offer a virtual office hour. If you have never been here before, this is your chance to get your questions answered. Type them in the chat and we will do our best to answer as many of your questions as we can, specifically focusing today on pre-calculus and algebra topics. So think about this as your virtual office hour. I'm here to answer your questions. Don't be shy. Drop them in the chat. And to kick things off, I wanted to start by talking about a question that didn't get answered in my previous live, and that is looking at logarithmic equations with logs. For example, if I had the log base 4 of x plus 3 plus the log base 4 of x minus 3, and I told you that equals 2, we can solve this equation for our x to see what's going to make this relationship true. The first thing we're going to do to help us out, though, is we're going to combine these two logs into a single log using our log properties. Because logs are actually fancy exponents. Logs are exponents. When we have the same base multiplied together, we end up adding the exponents. So we can use that same relationship backwards. Added exponents become a log base 4 of x plus 3 times x minus 3. We can multiply those exponents together. Now, whenever we're solving an equation, if we can't solve it as a log, we change it into an exponent. If we can't solve it as an exponent, we change it into a log. So let's change this log into an exponent. The base is 4, the exponent is 2, and the inside stuff is x plus 3 times x minus 3. Then all I have to do is just multiply this all together. 4 squared is 16. And this is a difference of squares. It's going to be x squared minus 9. And so if we want to get our final solution, we're going to set it equal to 0 so that we can factor and solve the resulting equation. Subtracting 16 from both sides gives me x squared minus 25. This, again, is a difference of squares, but this time with 25 as our square root is 5. It's going to factor to x plus 5 times x minus 5. We know that if two things multiply together to equal 0, one of those two things has to be 0 as well. So that means either the x plus 5 is equal to 0, or the x minus 5 is equal to 0. What's nice about this is it solves really quickly. Subtracting 5 tells us x is negative 5. Adding 5 tells us x is 5. And we get our two solutions. Or do we? I want to be careful, though, because we are talking about logarithms. When we get our final answers, we have to check to make sure that we don't get any illegal logs. Logs cannot have negative inputs. They can't even have a 0 input, actually. So if I put negative 5 into here, negative 5 plus 3, that's equal to negative 2. We can't have a negative inside of a log, so this one is what we call an extraneous solution. It's a fake solution. It doesn't count. Let's test the 5 to see if that one works or we have no solutions. 5 plus 3 is 8. That's a positive. We're good. Put the 5 in the other one. 5 minus 3, that's 2. Also a positive. We're good. So x equals 5 is actually our only solution to our logarithms. So that's our start with our pre-calculus office hour. For those of you that are logging in, welcome. We are so excited that you have joined us. I'm at Wallace Dem here on behalf of Chegg to answer your questions about pre-calculus and algebra. So what do you want to know about? Do you want to know about composition of functions? Do you want to know about complex numbers, inverse functions, exponential functions, radical equations? Lots of great topics that we cover in our office hour today. Amortization. That's a finance question. We can do exponential growth, though, which is closely related to amortization. Not exactly what you're asking for, but you're going to have to ask the econ guy for an amortization table. I'm going to take a look at exponential growth. Let's say that we have an investment of, let's say, $10,000. And it's going to grow at 8% interest, compounded monthly. For how long do we want to leave it in the bank? Let's put it in the bank for 20 years. There is a formula for compound interest that you probably don't need to memorize. You might want to be able to look it up. But the formula for compound interest is the future value, and every book uses different variables. So I'm just going to use convenient variables. But as long as we know what they mean, the future value in 20 years is equal to the principal value or starting value times 1 plus the interest rate as a decimal divided by the number of compounds in a year raised to the number of compounds in a year times the amount of time that investment sits there. So what we're going to do is go through and plug in this information. This $10,000, that's our initial investment. That's our P. Our principal investment, we're starting with that much. 8%, that's our interest rate. We have to write that 8% as a decimal. That's going to be our R of 0.08. It is compounded monthly. That means the bank is going to put interest into the account every month. N is the number of things in a year. The number of months in a year, N is 12. And then the 20 years, that's our time. So let's plug those things into our equation and see what we end up with. Future value is what we're looking for. P, we're starting with $10,000 times 1 plus the interest rate is 0.08 divided by the time, divided by the number of things, which is 12, raised to the 12 times our time, which is 20. It helps, by the way, to put this exponent in parentheses because a lot of calculators will get you in trouble if you don't put those in parentheses. So please do. And then we go to our handy-dandy calculators because I cannot do that in my head. Let's see what that's going to equal. We've got $10,000 times 1 plus 0.08 divided by 12. And then we're going to raise that to the 12 times 20 power. And wow. How much money do you think we gained? I know I dropped my calculator. While I pick that up, how much money do you think this is going to be after 20 years? Put your guess in the chat. See what we come up with. Or did you actually calculate it? No cheating. The future value, if you put this $10,000 away for 20 years, is, it fell off my calculator. There it is $49,268.03. Your $10,000 has almost been multiplied by 5. That is huge. I think it was Einstein that said the strongest force in the universe is actually compound interest and how fast it grows. Very, very cool. I got some more questions coming in about logs. So let's back up and take a look at some of those log questions. So many good questions. Which do we want to do? I think somebody had a specific problem I saw. Where did it go? There it goes from Duvalug. Log base 4 of x squared minus 9. Let's take a look at that. Thank you. Got lost in the scroll, but we found it. By the way, as we solve this question, if you have a question from your pre-calculus or algebra class, stick it in the chat and we're going to do our best to answer as many of them as we can. I saw a request for polar coordinates. We can take a look at that as well. So the problem was log base 4 of x squared minus 9. And my guess is what we want to do with this is we want to expand this logarithm into 2 logarithms. Well, we can't do that with plus and minus. You cannot, do not ever do this. This is bad. This is wrong. Don't do this. I see this all the time. It's bad. Don't do it. You distribute the log through, and I see people write log base 4 of x squared minus log base 4 of 9. That's bad. That's wrong. We don't do that. You cannot distribute the log. Every time you distribute a logarithm through parentheses like that, a kitten dies. Don't kill kittens. It's terrible. No. What we can do is split up logs that have factors or things that are multiplied together. So we need to factor what's inside this logarithm to correctly expand it. So we've got log base 4 of x squared minus 9. You should recognize that's a difference of squares. It's x plus 3 times x minus 3. Now remember, a log is just a fancy type of exponent. When we have the same base that is multiplied together, we can add those exponents together. Just like when we say a cubed times a to the 4th, that's a to the 7th, where we add the exponents. We can add these logarithms together. So this is log base 4 of the x plus 3 plus the log base 4 of the x minus 3. So we can separate them out if we factor the logarithms. So I think that's what that problem was taking a look at and for. All right. Let's see if we've got another question. Can you do logs that don't have the same base? Yes, let's take that question because those equations become a lot of fun. We're going to take a look at the question. Can we do logs that don't have the same base? Let's try this one. Thought I wrote one down like that. I did. Let's do log base 2 of x plus 2 log base x of 8 equals 5. So question was asking, how do we handle logs of different bases? Who asked that question? That was at AHLY8. I don't even know how to say that, from TikTok. So thank you for the question. That's a really good question because we can't combine these logs because they have a different base. So what we need to do is we need to change one of the bases to match the other one. We have a change of base formula that says that if we have a log in base A of B, we can write that with a new base, any base we want, we'll call it C, of the input divided by log base C of the old base, which is A. So what we're going to do is we're going to take this log base x of 8 and we're going to change it to match log base 2. That way we can combine them together. So I have log base 2 of x plus 2 times, we're going to do a log base 2 of the tall number, which is 8, divided by a log base 2 of the base, which is x, equals 5. And now that everything is in log base 2, it's going to be easier to work with and handle. So what are we going to do to solve it? Well, for one, I really don't like fractions. They're the F word of mathematics. Unfavorable. So we're going to get rid of the fraction by multiplying every term by this denominator. So I'm going to multiply by log base 2 of x, multiply by log base 2 of x, and multiply by log base 2 of x. When I do, I get log times log. That's log squared. Log base 2 of x squared. Plus, these logs reduce out, so we have 2 log base 2 of 8 equals 5 times log base 2 of x. Let's take a quick moment to look at log base 2 of 8 and see what that means. Remember, a log is just a fancy thing for an exponent, and we can use that to help us reduce. So somebody put in the chat, what do you think log base 2 of 8 can simplify to? Give you 3 seconds, and then we'll work it out. Stick in the chat, what does log base 2 of 8 going to simplify to? 2 seconds, 1. Let's say log base 2 of 8. Let's say that's equal to m. If I take 2 and raise it to the m power, remember this is the base, m is the exponent, and 8 is the answer. 2 to what power equals 8? If you said 3, you're exactly right. This bit here simplifies to 3. So now my problem is log base 2 of x squared plus 2 times 3, which is 6, equals 5 times log base 2 of x. And this looks exactly like a quadratic equation. Remember, a quadratic equation has stuff squared and that same stuff not squared. If it helps, let's say u is equal to log base 2 of x. If that's the case, u squared would be log base 2 of x squared. Move over here, which means log base 2 of x squared is u squared plus 6 equals 5 times log base 2 of x. We know that's equal to our u. This is just a basic quadratic equation. We can solve it by subtracting those 5 u's from both sides, and we get u squared minus 5u plus 6 equals 0. And this factors quite nicely. By the way, if you want a review of factoring, let me know in the comments. Say, put in a comment, hey, Wallace, teach us about factoring, and I'll give you a quick factoring tutorial. Whatever topic from algebra and pre-calc you want to see, stick it in the comments. I saw a comment that was asking specifically about this one. Why do we need to multiply the other side by log base 2 of x when we did that up here on this blue to red step? Remember, with equations, whatever we do on one side of the equation, we have to do on the exact same thing on the other side of the equation. So because I multiplied by log base 2 on the left, I have to multiply by log base 2 of x on the right. All right, where did we leave off? We're factoring this expression. U squared is u times u. 6 is 2 times 3, and if they're both negative, that'll give me negative 5 in the middle, which means each one of these factors could equal 0. So either u minus 2 equals 0, or u minus 3 equals 0. Adding 2 to both sides, u is equal to 2, or u is equal to 3. But remember, we weren't actually interested in u, we're actually interested in a logarithm. So let's change the u to log base 2 of x is equal to 2, or log base 2 of x is equal to 3. Remember, a log is just a fancy way to write an exponent. The base of the log is that number, the 2. The answer is the exponent, in this case 2, and that equals x. 2 squared, we know that's equal to 4, so 4 is our first answer. Same thing from the other one. 2 is the base, 3 is the exponent, that equals x, and 2 to the third power, that's equal to 8. That is our second solution to this equation. Now, we always want to check with logarithms, make sure our answers work in the original problem, because logs cannot have a negative on the inside. So the 4 and the 8, if I put them in here, we don't end up with a negative, and so that indeed is going to be our solution. Why do we add a logarithm to make it complicated? I think what's odd about logarithms is the word log. Like, it feels weird to have words in our math, right? Normally we see a plus sign or a minus sign or a times sign. And really, the best I can come up with is we just ran out of symbols to use for the logarithm, because a log is an exponent. Let's take a look at exactly what is a log, because I saw somebody put a comment, isn't a log like something that just fell out of a tree? Well, not these logs. Let's take a look at the logs what logs really mean. So log, actually, let's start with this. Start with the familiar. Let's say I have some base. We'll call it A. And we'll also do it with numbers. Maybe we'll do it with the number 5. And A can be raised to an exponent. Let's call that exponent B. Just like I can raise 5 to an exponent. We'll call that exponent 2. This is going to be equal to some number. We'll call it C. Well, in this case, 5 squared is 25. These can be rewritten as a logarithm. And how it gets rewritten as a logarithm is the base of the problem is the base of the logarithm. So A, or in this case 5, is the base of the logarithm. What goes inside of the log is the answer. So this is the log of C, or the log of 25. But a log, and I say this all the time, a log is an exponent. A log is an exponent. So a log will equal the exponent every time. The log equals this exponent of B. The log equals this exponent of 2. So log base 5 of 25 equals 2 is the exact same thing as 5 squared equals 25. A log is an exponent. Excellent. I saw a comment from TikTok. Anthony Andrews wants to take a look at how we factor. Let's do a quick factoring review because that is really important to pre-calculus. But before I get to that, there was let's do this one first. Then we'll come back to logs. I saw another great clarifying questions about logs and notation. We'll come back to your question next at motion. So hang tight. We're going to get to that. But I want to talk about factoring because it is so important to our study of algebra and pre-calculus, and it comes up again in calculus and beyond. It never goes away. So don't just learn factoring for the test. Learn factoring and get good at it. It's going to help you a lot. Let's take a look at a problem like 6x squared plus 7x minus 3. Excellent. There's lots of different ways people use to learn how to factor. There's the box method. There's the guess and check method. There's the AC method. Each method has its pros and cons. And ultimately, I don't care which method you use as long as you can factor. But my personal favorite method of factoring is called slide and divide. Slide and divide is really nice because it works the same no matter what's in front of x squared. And some of the other methods, it changes with what's in front of x squared. How slide and divide works is we're going to slide this 6 over to the end of the negative 3. 6 times negative 3 is negative 18, which means we're going to first factor this easier problem of x squared plus 7x minus 18. This is not going to be the final answer, but it's an easier one to factor that's going to tell us what the answer is to the original problem. So the idea is we want to find two numbers that multiply to this last number of negative 18, but add to this middle number of 7. Well, 18 is 9 times 2. It's also 6 times 3, but if I do 6 and 3, I can't get the number 7. But I can get the number 7 with 9 and negative 2. And so my factors are going to be x with a positive 9 and x with a negative 2. That's going to factor this easier problem. Now, we can't stop there because we haven't factored the black problem on top. We factored the blue problem underneath it. And our goal is to factor the one written in black. I mentioned this method is called slide and divide. First thing we did is we slide the 6 over. The next thing we're going to do is we're going to divide by the 6. When I divide by the 6 on both of them, we're going to reduce those fractions, and whatever's left on the bottom is going to slide back in front of the x. So 9/6 reduces to 3/2. 2/6 reduces to 1/3. The 2 is going to go in front. The 3 is going to go in front. And so we have 2x plus 3, taking the reduced number. And the 3 coming in front, 3x minus the 1. And that factors the original problem. So we divide and reduce. 2 goes in front, 3 goes out at the end. 3 goes in front, the 1 goes at the end. That's called divide and slide. Great question came in from TikTok at Adam Befriel. Adam Befriel, could I have used the quadratic formula? No. Because to use the quadratic formula, it has to equal something. And the quadratic formula will tell you the answers if it was equal to 0. Since this one's not equal to something, all we can do is factor it. Because sometimes we have to factor things that don't have anything to do with it being equal to 0. And the perfect example of that is rational expressions. So let's take a look at a rational expression that's going to give us a chance to practice this factoring method of slide and divide. And I'm going to quiz you. I'm going to give you some things to factor, and I'm going to see if you can factor it yourself. So let's do x squared minus 6x plus 5 over 9x squared minus 1 times 3x squared plus 16x plus 5 over 2x squared minus 5x plus 3. Let's have lots of fun. Let's divide also. Let's divide x squared minus 2. That doesn't look right. Well, let's not get too crazy. We got so many other great questions to get to. I want to make sure we have time to do that. So if we wanted to simplify this expression, the quadratic formula is not going to help us at all because it's not actually equal to anything. But we still need to factor each of these terms, each of these factors, numerators and denominators. So in this first one, because there's only a 1 in front, the slide comes out really nice. We get 1 times 5, and that's x squared minus, let's see, I'm going to move over here. We'll show our work. That's x squared minus 6x plus 5. We're looking for two numbers that multiply to 5 and add to -6. Go ahead and put in the chat. Tell me if you can see the two numbers that multiply to 5 and add to -6. Did you come up with them? There's only one way to multiply to 5, actually. The only way to multiply to 5 is 1 times 5. To get -6 out of that, they both have to be negative. And so this first one is going to factor to x minus 1. Actually, I'll write it over here. X minus 1 times x minus 5. That's the divide step. Oh, that's the slide step. We still have to divide by that number 1 that's slid over, but dividing by 1 is not going to change anything. So this first numerator factors to x minus 1 times x minus 5. This denominator, though, is actually a special quadratic that we can factor. Because of that subtraction, and we've got something that is a perfect square on both sides, we know it's going to factor to the sum and the difference of the square roots. The square root of 9x squared is 3x, and the square root of 1 is 1. So 3x plus 1, 3x minus 1. Nice little shortcut. All right. These ones to factor, it's going to take a little bit more work, but we can do that. I'm going to slide the 3 over to the end. 3 times 5 is 15. So I'm going to first factor x squared plus 16x plus 15. 3 times 5 is 15. What are two numbers that multiply to 15 and add to 16? Well, if you said 15 times 1, you're right. That's going to be x plus 15 times x plus 1. But we've only done the slide. We still need to do the divide by 3. So I'm going to divide each of these by 3, which is going to give me, this one's going to reduce just to 5. This one doesn't reduce at all, so we put the 3 in front, 3x plus 1. So you see how that denominator moves out front, and anything that reduces keeps in that numerator. All right, so the top one is x plus 5 times 3x plus 1. Bottom one, we're going to do that exact same thing. We're going to slide and divide again. So we've got the 2 times 3, that's going to be 6. So x squared minus 5x plus 6 is the easier problem we're going to factor. What's something that multiplies to 6 and adds to negative 5? Well, be careful. Last time we did multiplies to 5 and adds to negative 6. That's different. 6 is 2 times 3. And if they're both negative, it gives me negative 5. So we've got x minus 2 times x minus 3. But don't forget, we still have to divide by that 2 out front. So I divide these numbers by 2. And if it reduces, that's great, x minus 1. Whatever doesn't reduce, that denominator moves out front, and we get 2x minus 3. So this becomes x minus 1 times 2x minus 3. All that work to factor so that we can reduce, because the only thing we can actually reduce are factors, things multiplied together. So if I see a factor now on the bottom and the top, it can reduce out. I see a factor of 3x plus 1. That can reduce out. And nothing else matches. So for our final answer, this simplifies to x minus 5 times x plus 5 over 3x minus 1 times 2x minus 3. That is our solution. And the quadratic formula can't help us there. The quadratic formula is limited to when equations equal 0. It's a really niche way to factor expressions. I really love slide and divide. It always works. And it makes it easier because you don't have to worry about a not being equal to 1. Excellent. All right, let's see if there's any other questions that we can answer that have come in. Remember, we are here to answer all of your questions in the comments about pre-calculus and algebra. There are lots of great topics that we can take a look at. A lot of people seem really partial to the AC method as I'm looking through the comments, and that's great. The AC method is another way to factor. Why don't we take a look at how the AC method works so that we can compare it to slide and divide? Because for me, what's important is you need to know how to factor. It doesn't matter which method you use. So if you like the AC method, that works really great. And it's kind of similar to slide and divide, actually. So let's say we've got 7x squared plus 15x minus 8. The reason it's called the AC method is we often call these numbers A, B, and C. And so the AC is A times C. 7 times negative 8 is negative 56. And then we're going to add to 15. Notice those are the same numbers you would end up with if you did slide and divide. They're very closely related. So we're looking for two numbers that multiply to negative 56 and add to 15. Positive 15. Well, that one's not jumping out to me as obvious. Let's see, 56 times 1, 28 times 2. It's not divisible by 3. It is divisible by 4. 4 times 1. Uh-oh, is this one not factored? 4 times 16 divided by 4 is 4. 4 times 14. I don't think this one factors. Did I write the problem down wrong? Well, that's incredibly disappointing. Somebody stick it in the comments if you're seeing it and I'm missing it, but I don't think this one factors. Let's do another one. That's the problem with factoring, is not everything factors, and it's problematic. Let's do the one that we already did, because we know this one works. 6x squared plus 7x minus 3. And much like, so how the AC method's going to work on this is we're going to multiply to 6 times negative 3. That's negative 18, A times C. We want to add to the middle number of 7. Again, just like slide and divide, we're just not doing the sliding part. It's going to be 9 and 2, where the 2 is negative. How the AC method works is it says, okay, we're going to take this 7x in the middle, and we're going to split it up into 9x and a negative 2x. So now we have 6x squared plus 9x minus 2x minus 3, and that gives us 4 terms that we can factor using the method of grouping. Grouping says we're going to just look at the left and right side. What's the common factor? These two have a common factor of 3x, leaves behind x plus 3. And on the right, we always factor out at least the sign, more if we can, but there's nothing in common here, so it's going to be 2x plus 3. And did you see my mistake? 6 divided by 3 is 2, so we should have a 2x there. Yeah, excellent. Where did I get the negative 2 from? Great question. The negative 2, remember we were multiplying to 18 and adding to 7. So 18 is 9 times 2. And the way we can get to 7 is if I subtract 9 minus 2 to get to 7. So I needed the 2 to be negative. And that's how we split up our terms. All right. The nice part about this grouping method is if you've done everything correct up till this point, you should have a binomial that matches on both sides. That's one of the factors, 2x plus 3. The other factor is what's left. 3x and a minus. Remember, there's always a 1 in front of everything. 3x minus 1, and then it is factored completely. So that's the AC method. Works really similar, a lot in common with slide and divide because we're really trying to do the same thing in the end. Excellent. Great questions. I want to go back, though. There was an amazing question about logarithms. Where did it go in the chat? A lot of love for the AC method in the chat. Aren't logs base 10 and ln based e inverse of exponents? That came from @motion quite a while ago. Sorry that I got away from that. But let's take a look at that, going back to the logarithm discussion. It must be about logarithm chapter time in your pre-calculus and AP pre-calc classes, because we've got a lot of great log questions. Great question. Log base 10, let's say of x equals 2, and maybe log base e of x equals 1. Or equals 0. Let's make this one equal to 0. So 10 and e are numbers that come up a lot when we're doing applied mathematics. 10 comes up a lot because of astronomy, physics. We're doing things on a very large scale, and so you've got scientific notation, and you're multiplying by 10 to get various powers of 10. We make graphs with scales that are logarithmic based on powers of 10. If you're talking about earthquakes, they're on the Richter scale based on powers of 10. 10's a really common base. It comes up a lot. And what you find is mathematicians are incredibly lazy. So they're not going to do any more work than they have to do. That's one of the reasons we have math patterns and formulas. So one way we get lazy here is because we do log base 10 so often, you'll often just see this written as log of x equals 2 with no base. No base implies the base is 10. So if I want to change this to an exponent problem, the base is 10, the exponent is 2, and the input is the answer. So here in this case, x turns out to be 100. Also, e comes up a lot just in nature. It comes up a lot with compound interest. It comes up a lot with population growth. It comes up a lot in logarithmic growth where you're tracking diseases over time. And you might have heard about this disease called COVID from 5 years ago. Logs were used to track that disease with a base of e. Base e comes up a lot, and so we call it the natural log of x equals 0 in this case. So if we see ln means natural log, it means base e. So if I were to convert this one to an exponential, the base is not written, it's e, the exponent is what it equals, And then that's what our x is. In this case, anything to the 0 power is 1. And so x in this case would be 1. So that's what's going on there with the log base 10 and log base e. They are actually special logs. They aren't the only logs. You can do logs and base anything you want, but that's kind of a nice look at why those get used all the time. Let's see. Let's talk about another use of logarithms, shall we? By the way, as we put up this other use of logarithms, we're going to do exponential equations. Remember, this is your office hour to answer your questions. So what are you doing in your pre-calculus and algebra classes? If you're doing something exciting, you have questions on them, you can stick them into the chat. And actually, before I go off to my exponentials, Drew, Drew asked a question very related to log base 10. Can it be another number? It can be equal another number. So if I have the log of 27 equals x, my calculator can actually do that because your calculator has a log button on it with no base written. That no base written is because it's assumed to be a base 10. So I can just put in my calculator log of 27, and when I hit enter, that tells me that x is equal to 1.431, we'll round it to 4. What this means is this x is really 1.4314 on and on. If I were to rewrite this as an exponential problem, the base is 10 because there's no base written, and this number is my exponent, 1.4314 on and on. And when I do that on my calculator, the answer should be 27. So let's try that and do it on the calculator, see what we get. So I'm going to take 10 and I'm going to raise it to the 1.4314 power. And when I do, remember I rounded that up, so it's going to be a little bit large. I get 27.002, which is pretty darn close to what we wanted. So that's log base 10. It's always a base 10, but the numbers can be pretty much anything that we want them to be to help us solve, which is really nice because logs help us solve problems that have exponents in them. For example, if I had 3 to the 2x power equals 7. Actually, let's just simplify this. We'll do a more complicated one in a minute. If we have 3 to some power equals 7, well, we know 3 to the first power is equal to 3, and we know 3 to the second power is equal to 9. Well, so the answer, the exponent has to be somewhere between 1 and 2, but we don't know exactly what it is. We can solve that by rewriting this as a logarithm problem, because if you can't solve it as an exponent, we rewrite it as a log. This time the base is 3. The input is 7, and that's equal to x. So x is whatever log base 3 of 7 is. But we have a problem. We can't figure out what log base 3 of 7 is using our calculators, unless you have a big fancy calculator, but I'm assuming you don't. And the reason you don't is because it's very easy to convert this using what we call the change of base formula. The change of base formula says I can take the log of base anything of some number, and we can write it as log base something else of the input divided by log base something else, same something else, of the old base. That's the change of base formula. So because on my calculator I have a log button, base 10, and I have an ln button, base e, we can change to one of those to calculate what x is going to be equal to. Let's do log base 10. So we'll do the log base 10 of the tall number of the input divided by log base 10 of the base, which is 3, and that's equal to x. And that I can do on my calculator. Let's figure out what it is. We expect it to be between 2 and 1. Log of 7 divided by log of 3. Be very careful with parentheses A lot of your calculators will open a parentheses as soon as you hit the log button. If you forget to close it after the 7, it's going to think the other part is inside your answer as well. And I'm coming up with x is equal to 1.7712. So that means if I do 3 to this exponent, the answer should be 7. Let's try it out. 3 to the 1.7712 power. The answer I'm getting when I do that, 3 to the 1.7712 power, is 6.99967. And that's just off by a round off error because we had to round our answer because it's not a pretty number, but that's essentially 7. Why can't I do log base 3 of 7? Great question. Why can't I figure out what log base 3 of 7 is? The reason for that is your calculator doesn't have it programmed in there. That's all it comes down to. Your calculator knows that it's easy to do this change of base formula. So instead of having to program into the calculator every single possible base in the universe, because you could even have a decimal number for a base, it would take up so much memory to store all of those in your calculator. It's much more efficient to just have log base 10 in your calculator, and you know you can switch back and forth between log base 10 and the others. Excellent. You're welcome, Drew. Thanks for the question. It was really helpful. What other questions do you have about trig and algebra? I'm sorry, not trig, pre-calc and algebra. What do you want to see? Let's see. I'd like to do a composition of functions. Nobody's asked about functions yet. So log 3 is equal to 10. Are you asking if log 3 what the base is? Because here the base is 10 if it's not written. So Drew was asking about does log 3 mean base 10? It's not equal to 10, the base is 10. What we're saying is 10 to some exponent is equal to 3. And log 3 is going to tell us what exponent on 10 gives us that. And now I'm curious, Drew, you got me all the good questions here. If I do log 3 on my calculator, it's going to give me 0.4771. And so that means 10 to the 0.4771 is equal to 3. Excellent. All right, let's do an exponential equation. I'm sorry, we already did an exponential equation. I'm out of order here. Let's solve a composition of functions. Let's say f of x is equal to 2x minus 5, and g of x is equal to x squared minus 3x plus 1. We're going to find f of g of x. So function notation is a really important topic that comes up in pre-calculus. Setting you up for calculus, we need to really get used to recognizing the structure of a function. F of g means we're going to take the function f and we're going to stick the g of x function inside of it. So this is the g of x function. It's going to go inside the variable in the f of x function. So the f of x function here is 2x minus 5. But what's going inside the x is that g of x, that inside function. So this whole thing, the x squared minus 3x plus 1, goes into the function. We can do a little simplifying just to clean it up. Distribute through 2x squared minus 4x plus 2 minus 5. Let's combine like terms at the end to get a final answer of 2x squared minus 4x minus 3. And this is what f of g of x is equal to. Pop quiz for you. I want you to put your answer in the chat here. If f of g of x is that, does that mean that g of f of x is going to be the same thing? Do we get the same answer if we switch the order? Put in the chat, what do you think? 3 seconds to give me an answer. Yes or no, are they the same? 2 seconds to give me an answer. Are they the same? G of x and f of x. Got your guesses down? Let's actually do it and see what we get. I'm going to erase my colors here because I'm going to color code everything again. Now, when we see g of f of x, that means g has the f of x function inside of it. So now I'm going to take the f of x function and we're going to stick it inside each of those variables. So the g of x function, it's something squared minus 3 times something plus 1. That something, what's going into the function, is the f function. The f function is 2x minus 5. And it goes into both spots. Then we can simplify this to see if we get the same answer. Someone thinks I might have a slight mistake. What did I do wrong? I'm not seeing a mistake, but if you see a mistake, let me know detail in the chat what I did wrong. I want to make sure I get it right, but I think we're still good. We're going to square this 2x minus 5. When we square the 2x minus 5, there's a shortcut that we can use. It's really nice. We can square the 2x. That gives us 4x squared. Then we multiply the pieces together. That's negative 10x. And we're going to double it because it shows up twice, negative 20x. And then we square the 5 to get 25. Then I'm going to distribute the 3 through. That's going to give me negative 6x plus 15. And we still have this plus 1 at the end. Let's combine like terms. There's 4x squared. See, a negative 20x and a negative 6x is negative 26x. 25 plus 15 plus 1 is 41, I think, if you trust my mental math. But what we see is g of f of x and f of g of x are actually very different situations, very different problems. A question came up too about do I distribute first or do I square first? Technically, if we want to be really technical, you should always do the exponent first. So you should always do the squaring first. After that squaring's done, then we can multiply. But because this wasn't multiplied by anything, we can kind of get away with doing both at the same time. That's a great question. Who comes first? It's order of operations, which depending on your textbook, you either have PEMDAS or GEMDAS. P means parentheses, G means grouping symbols. They're both kind of saying the same thing. But the squaring is the exponent step that happens before the multiplication and division step. So we want to make sure we get those in the right order. Did I write negative 4x instead of negative 6x? Oh, I did. You're right. Who was it that caught my error? A lot of you caught my error. Hey, hello, Math Playground. Hey, I follow you, so I'm excited to see you here. Yeah, 3 times 2 is 6, not 4. How the heck did I get 4? Sometimes the hardest part of a math problem is the mental math. There you go. Good catch. Thank you for letting me know. I think Ubaid Ula also got that for me, so thank you for catching that error for me as well. Excellent. Well, we are getting close to out of time. I think I have time to answer maybe one more quick question. So why don't we do a little bit of work with, I don't have time to do those problems. Let's do some complex numbers. Complex numbers are a huge topic in pre-calculus. And then when you get to trigonometry, you get a look at how complex numbers can work in polar coordinates. Complex numbers are centered around this idea that I is the square root of -1, and more specifically, I squared is actually -1 is really how we define it. So if I have got an expression that I want to multiply, maybe 2 plus 4i, or 4 times the square root of -1, and 7 minus 3i, or 3 times the square root of -1, we can actually multiply this out much like we would multiply with parentheses, with FOIL, with distributed, whatever method you want to call it. So we can multiply this 2 distributed onto the 7. 2 times 7 is 14. We can distribute the 2 onto the -3 to get -6 of these i's. Treat the I just like a variable right now. We know what it equals, but treat it like a variable right now. Then we've got 4i times 7 is 28i. And 4i times -3 is -12i squared. The thing we're going to do different with I that we don't do with normal variables is whenever we have I squared, that's equal to -1. And multiplying by -1 changes the sign of the number. So now it's a plus 12. Then all I have to do to finish is combine like terms. 14 plus 12 is 26. And -6i plus 28i is 22 i's. And that gives us our solution for the complex numbers. Now, question came up, and I think we have time to answer it really quick, is what about the magnitude of the complex number? Let's take a look at the magnitude of a complex number. Magnitude is a special property of complex numbers, and we don't have time to really get into the graphing of it and how it works, but it's really cool. But the idea is if I have a complex number, a plus bi, the magnitude of that complex number is the square root of a squared plus b squared. It's really telling us the distance. That's why it looks like the Pythagorean theorem. It's the distance the number is from 0. And it's kind of weird to think about like 5 is 5 to the right, but where is square root of -1 from 0? And so there's some graphical ways we can look at it, and we can probably talk about it next week because we are here every week at this time, 5:30 Pacific time, not 5:30, 6:30, 6:30 Pacific time, 9:30 Eastern time to answer your questions. So if I've got the complex number, let's do 5 plus 12i, and I want to see the distance this number is from 0, as weird as that is to think about, all I have to do is square the first number, square the second number, and take the square root of that. That gives us the magnitude of that complex number. And 25 plus 144 is 169, which has a beautiful square root of 13. And so we would say the magnitude of that complex number is 13. Well, I can't believe we are already out of time. We've been having so much fun running through these problems as quickly as we can, answering as many of your questions as possible. Thank you for joining us. I hope you can come join us again next week. We are here every week on Wednesday night, 6:30 Pacific time, 9:30 Eastern time to answer your questions about pre-calculus and algebra. But these aren't the only lives that Chegg is doing. Chegg is doing all sorts of lives to help you with your courses and to be successful in your classes. So I want to encourage you to scan this QR code to stay updated on future office hours. There's calculus office hours, there's trigonometry office hours, there's also chemistry, economics, and more. Scan the link to stay updated. Of course, make sure you're following Chegg on TikTok, on Instagram, on YouTube, on Twitch, so that you get up to date on all the exciting things Chegg is doing as we help you be successful in your courses. Remember, we're here every week at this time. So until then, happy studying, everybody. It's been a blast doing this live with you, and I look forward to seeing you again next week.